This video is going to look at wave properties and specifically how waves interact with things. And all of this is because waves aren't physical things. So waves aren't objects, they're phenomena. They're things that are happening. They're interactions of lots of physical objects that create this phenomena. So that means some special properties emerge. The first that we're going to talk about is interference. And so two waves that collide, and if you remember our definition of collide is two objects trying to exist at the same point at the same time. Well, two waves collide, they add together or they combine. They don't hit or bounce. And this is again because they're not physical objects. So two physical objects can't exist in the same place. Two waves can, because again, they're not physical objects, they're phenomena. Now, there's two types of interference that result from these waves combining or being at the same spot. You can have constructive interference, and this is when waves combine to create a greater amplitude. And you can have destructive interference. And this is when waves combine to create a smaller amplitude. So if you look down here at our diagram, we've got two waves. In the first one, you see that we've got a peak and our peaks and our valleys lining up. And so we get even bigger peaks and even deeper valleys. Because basically wave 1 for this first third says go up, wave 2 says go up, and so the wave, or whatever the medium is, goes up twice. It goes up twice as much. Then in the middle part, the first wave says go down, the second wave says go down, so the medium goes down twice as far. In our second picture here, the waves are saying opposite things to the medium. So in the first section, the wave says do a downslope, the second wave says do an upslope, and what happens? They cancel out, because the medium does both. It goes up. If you imagine kind of the very, very first point right here, it goes up and it goes down by the same amount, which means those two changes cancel out and it stays in the middle. And that's why you see kind of down at the bottom a flat line of the resultant, the combination, is all the ups and downs cancel out. And then this is depicting something else that we're not worried about in this, so really just be looking at those first two. The first one is an example of constructive interference. The second is an example of destructive interference. Next, we're going to talk about resonance, and this is where you have a wave that is kind of trapped. So resonance. So if a wave is trapped between two boundaries for whatever reason, you saw this in the wave model lab, where when you had the compressed spring, that compression has to stay in the spring, so it's going to go back and forth. If this is just right, the wave size, the wave frequency, all these things are just right for the space that it's trapped in, it will alternate between constructive and destructive interference. And this is what we call resonance. And resonating waves are also known as standing waves. And so what's happening here is if you've got a wave trapped, what happens is, imagine I've got like a string, and I put a wave into it that's this big. And now that wave pulse is going to travel along the string until it hits the wall, and then it's going to bounce and come back. So you can imagine it goes, it hits the wall, and then it comes back like this. And the reason it's flipped is a technical reason you don't need to worry about for this class, but it does kind of flip backwards like this. Now, when this wave comes back, it's going to travel all the way to the left wall, hit the wall, and bounce back. And now if there's a bunch of waves in here, such that they either line up or don't. So imagine this is that. You'll notice that the bouncing back waves will cancel out with the waves that were traveling forward. Because again, it goes in, and then we see an up matching with a down. And so this would be destructive interference. And then for reasons, again, that we're skimming past, if you want the details, come talk to me. But what ends up happening is when this all fills up, it'll actually alternate between the waves will line up perfectly, and then they'll line up perfectly to destroy. And what you end up getting is, if you originally put in a wave that's this tall, you'll see it become waves that are twice as big, and then it'll go away completely. And this is something we'll demonstrate in class, and I'll talk a bit more about the details of what's happening there. But this is kind of the broad overview to get you started on thinking about resonance. Next, we're going to talk about refraction. And refraction is when a wave moves between media, so from one substance to another, or from one density of whatever liquid or solid to another. So when waves move between media, they change speed. And this is just because the particles are arranged differently, so that transfer of energy will be faster or slower depending on what medium you're in. And this causes the waves to, what word did I use here? To bend and travel in a new direction, and this is known as refraction. So refraction is when you can imagine a wave is traveling along and it changes direction. The way that I can kind of illustrate this for you is, imagine you've got a sidewalk. So this is concrete. And then you've got some grass next to it. And then you've got some tube or some wheels, like some small car that's rolling along. So let's call it a small car here. So it's got all these wheels. Now, it's traveling in this direction. Now, what happens when one of these wheels goes onto the grass? Because you can see it's eventually going to end up on the grass. Well, it's harder for the wheel to roll in the grass, so that part of the car is going to slow down. So when this front right corner of the car hits the grass, those wheels are going to slow down and they're going to travel less quickly. These are going to keep traveling quickly, and what that ends up doing is you get sort of a turning, and then the car travels in this direction on the grass. Once all four wheels are on the grass, they'll all move at the same speed, and it'll continue going straight again. But while this wave is kind of transferring from the concrete to the grass, it's going to get this turn happening. Now, this will only happen if it's going at an angle. If it's going straight, right, the front two wheels both hit grass at the same time and they don't change. So it's just if you're traveling at some angle, the wave will bend the direction that it's traveling in. Because again, part of the wave will keep moving at a faster or slower pace than the others. Diffraction is similar idea of dealing with the bending of waves, but it's a more complicated phenomena. And this is what happens when waves move through an opening. They will also bend. So when waves move through an opening, they bend, and this is called diffraction. So this isn't moving from one substance to another, this is moving through an opening. So if there's a gap like this in, say, a pool of water, and then you send a bunch of waves, so imagine these are the peaks of the waves. So in between these lines are the low spots of the waves. So it's kind of coming in and out of the screen. So there's a high point, a low point, a high point, a low point. Well, what happens is when you hit this gap, well, that wave can only go through the hole, right? It's going to bounce off of the wall. But what you'll see on the other side of the gap is those peaks end up doing something like this. They go out in kind of a arc. Now, the closer the size of the opening to the wavelength of the wave, the more rounded or the more of a U shape you'll get after passing. So if you'll notice here, these waves and this gap are about the same size. If it's a really big gap for the same size, same wavelength waves, what you'll end up seeing on the other side is something more like this. So it's going to be mostly flat, but then you're going to get some bending kind of towards these edges here. And this isn't the best example, but you can kind of think about it like the waves will want to go along the wall as well as go forward. So if they're kind of close together, then the only way it can go forward and go along the wall is by curving. That's not a perfect way to think about it, but it is close enough. What's also interesting, just as a last aside, is if the gap is really small, but the wavelength is really big, the same thing will also go through pretty straight. So on the other side, we'll get mostly straight waves with maybe a little bending at the edges. So when they're really close, you get a lot of bending. When they're big difference, you don't get much bending. They come through pretty straight. Now, quick note on that and why I've kind of glossed through it quickly. Mechanical waves can diffract and refract, and they do, but we're much more commonly talking about these with light. And that's where we'll mainly talk about them in this unit, is how they react with light. And that's because light is an electromagnetic wave. So light is not a mechanical wave. It doesn't pass through a physical substance. It passes through this electromagnetic field, so we call it an electromagnetic wave. Again, that will come up later. Don't stress too much about it at this point.